All right, hello everyone. So this is the final tutorial, and as you know, it's not being recorded live because of the quiz. So hopefully you have a chance to watch this. So this is chapter 13, which gets a little bit more into radiation, and specifically in this tutorial, we're going to be covering view factors. So essentially what a view factor is if you have a object that's emitting emissively, so you have some sort of temperature and this causes some sort of emission, as we know. Some amount of it is going to strike this surface. So if this surface is I and the surface is J, and then a lot of it is going to go outwards and probably strike other surfaces, maybe walls or whatnot, whatever's in its range. And so essentially the view factor, we call it the view factor from I to J. So of what's coming off of here, how much of it is hitting here. And that's actually exactly how it's defined. So how much energy emitted by I, which strikes J, divided by the total energy. Okay. So the formula for this is fairly complicated, but luckily we won't actually use it, but I'll just give it this once so we have it. Okay, so it's a fairly complicated formula, but luckily we won't actually be using this. Instead, we'll be using some more practical methods. So first method would be table 13.1. So if you have these specific cases, like two squares close to each other, this case I showed at the beginning, and there's more in your textbook, you can use these equations, and while these equations are long, it's just a matter of plugging in all the numbers. You can also use a similar situation where you have these specific cases. You can use these charts to find your view factor. And then our third method is if you have infinitely long or roughly infinitely long objects. So in this case, it's shown as these two lines, but the idea is that they're kind of going into the page indefinitely. You can use this cross-string method, and we're going to do an example, so we'll cover the method when we do that. So 13.1 are cross-stringed. All right. So there's just a couple rules that are good to keep in mind while we do this. The first thing is that our f from I to j is not necessarily equal to our f from j to I. So you can think of this as if you had this kind of small object and it was close to this super large object, then you can think that a lot of what's emitted would actually be absorbed by this. So maybe our view factor would be quite large, but then this emitting, only a small amount of it would be hitting this plate. So that will help you understand why. But there is a relationship. So if you have one of the factors, you can find the other one. So AI Fij is equal to AJ Fj to I. So if you have your view factor from the small to the big, you can use this area ratio to find from the big to the small. And the second one that's important, and I'm running a little bit out of room, so we'll just kind of go over here. is our summation method, or our summation rule, which is the sum of all the view factors from I to j, where you can think of a number of j's that you're trying to find is equal to 1. And you'll remember that in a lot of the questions we covered with radiation beforehand, we always used to say that the surroundings were some temperature. And often when it was drawn, you would have your kind of object, maybe it was a pipe or something, and then you would draw kind of like this, and you'd say your surroundings were some temperature. So the idea here was that our view factor was 1. So that was the kind of thing that we were assuming, that we never said explicitly because we're only now learning what view factor is. So those are the main rules. This is reciprocity. And this one is the summation rule. And there's a couple other rules like symmetry you can look up in your book, but these are the most important ones. And then one other thing that I just wanted to include here is just keep in mind that your view factor from one shape to itself isn't necessarily 0. So if we have a concave surface like this one, it can actually emit to itself, and in which case there is an F I to I, or as they show here, F3 to 3. So don't forget that that is possible. And then when we actually go ahead and use it, the idea is that our total amount of heat transfer that's going from one object to the other, or our total emissive power, would be your emissive power formula times your area times your view factor. So this is how much power is pumping from one object to the other, but often what we're interested in is the net power. I know it's a little messy, but in this case, what we're looking at is how much radiation is being transferred from one object to the other, minus how much radiation is kind of being pushed back. So the net amount of heat gain you would get. And in this case, what we would be doing is taking your emissive power times your first area times how much is being transferred to 1, and then we're going to subtract how much is being pushed back from 2 to 1. And so what's nice about this is that we can just apply our reciprocity law that we talked about earlier, and we only actually have to use the one view factor. So we talk about our A1 or F1 to 2, and then we'd be able to take our difference of temperature. So this is how we are going to use the view factor. So in the questions we're covering in this tutorial, it's only going to be just solving for the view factor because that's the new concept. Okay, one more thing I just wanted to talk about very quickly is because we're in building engineering, one question we can ask is why, I guess, does this matter? And one kind of interesting example, of course, radiation is often something we consider with the radiation of the sun. But one kind of interesting example is you've had of a person maybe sitting here working at their desk. Often we've talked about before where our surroundings are some temperature, but in offices there's a very obvious situation where one part of the surroundings is not the same as the others, and that's with the big window. And this can actually be a problem, especially as in newer buildings, windows get really, really large. If it's very cold outside, like minus 15 degrees, then the temperature of the inner glass can often be quite cold. So let's say this is like 10 degrees and the room temperature is 21. So this 10 degrees, people will actually lose heat through radiation directly through the window. And it's not something we think about a lot, but it is actually something that makes a pretty big, matters quite a bit. So if you look at this person, the breakdown of how much energy they're losing everywhere. So they have some evaporation through their sweat, a little bit of conduction of the floor. I think we usually ignore that. But what's always interesting to me is that the convection is fairly small and the radiation is fairly large. So big windows, even if your air temperature is maintained through your HVAC system, can cause discomfort. So hopefully that's a little bit more of a practical example. And I'm sure in your other classes you've seen, there's a couple view factor calculations that are specifically for these situations that are developed within the building engineering community. These ones that we're going to learn today are a little more general. Okay, so all that said, let's get into our first question. So in this question, we have this enclosure. We have areas 1, 2, and 3, and we want to use a length to diameter ratio. K is equal to L over D. So we know the length, we know the diameter, K equals L over D. That's just to kind of end up with this very neat function at the end. But aside from making it look pretty, that doesn't really do that much as far as I know, at least for this question. The expression for the view factor between the base and the side. So we want to find an expression for the view factor between the base and the side. So F 1 to 3. So you can think of it as this is emitting, and we want to know how much of it is hitting this side. And then we want to see what happens when L over D is L is equal to D. So essentially when K is equal to 1. So in this question, this is one where we have the situation where we're going to look at what options we have as far as cases, or if this fits one of our cases, and then we're going to calculate our answer. And when we look at our cases, and we can do that very quickly back where we started. Starting with table A1, we can see that we do have this coaxial disk. So we have what is going on a little bit in that question, but of course in that question, we're more interested in what's hitting the side. And I did mention there's more, so you'd want to look through all of them, but in this case, we don't have this case. We don't have a case where we have a circle and then its cylinder. But we can take advantage of our summation rule. So if we can find how much of this energy goes here, we just know that the rest of it strikes the side. So this is an example of the summation rule where we say F11 is equal to, F11 plus F12 plus F13 is equal to 1. F11 is a good thing to write just to remind yourself that things can have heat transfer to themselves, but anytime you have a flat surface, F11 is going to be equal to 0. It's only concave surfaces where a view factor will happen to itself. Therefore, we know that F13 is equal to 1 minus F12. Okay, so we're going to take our coaxial plates, table 13.1. We're going to say our I, that table works off of the IJ method, so our I is going to be our 1, our area 1, and we're interested in comparing it, how much it exchanges with our J, which is 2. So we plug in the long equation in the table, we get a half S minus S squared minus 4 D2 over D1 all squared to the half, and that's it. Okay, so one thing we know, our A1 and our A2 are the same size because it's a cylinder. So we'll just simplify this down a little bit. Okay. And if you look at that table, we also have an expression for S. So again, this S is just to make the equation look a little nicer, but in table 13.1, they tell you what S is, and it's this. Simplifying again, so again, we know R1 is equal to R2. And so if these two are equal, then dividing them is equal to 1. So if you split this up, you get 1 over R plus 1, or 2 plus 1 over R squared, so R being R1 or R2. And we're going to Okay, I got confused for a sec, but with the magic of cutting down the video, you guys don't have to wait for me to find the answer. So this part was a little confusing, and it's because, again, back in this table 13.1, they're actually defining this capital R as equaling R over L. So this capital R refers to the radius divided by the length. And so that's how they're able to make this simplification. That's how this 4 gets up there. And then they cut it down to the 2 plus 4k. Okay. So now what we want to do is combine those two equations together. So our F1, 2 is equal to 1 over 2 plus 4k squared minus 2 plus 4 squared minus 4 some brackets here. Half. Okay. And we're able to simplify this down to 1 plus 2k squared minus 2k. And if you're a little lost at this point, that's okay. This question is just very symbolic, so it can be hard to follow. Just remember that k is just this thing we've called L over D. So you may think, what is k? But it's just the ratio of our length over our diameter. And the only reason we're using that is because we want our final answer to be in k, in terms of k. Okay, so now is the part where we're going to actually try to find F1 to 3, which was ultimately what we were looking for in this problem. And remember that F1 to 3 is just 1 minus F1 to 2. This is our summation law. So 1 minus, and then in brackets, this. All right. And simplifying this down, we can get F13 is equal to k squared plus 1 minus 2k. And this is what we were looking for from the beginning. Yeah. Okay, so that was all for part A, and then for part B, we actually want to find a numerical value assuming that L is equal to D. And we said before, if L is equal to D, then K is equal to 1. So we're essentially just going to plug a 1 into this equation. And if you calculate that out on your calculator, you'll get 0.828, which was the answer to part B. Okay, so this question to me is a whole lot of algebra and not a whole lot of theory. Just keep in mind that essentially what we were doing is trying to find the view factor here by taking this case we know, which is these two plates, using our table and just a whole bunch of algebra to get our expression between these two plates, and then doing 1 minus them to find what was left over. Okay, so that's question 1. And kind of method 1 with using these tables, and method 2 is the cross-string method. And the cross-string method is a little more versatile, but only for one specific case, and that's when we have infinitely long something. So this method, we have these two cylinders. Both of them are D, so both of them are the same size. In this case, our F12 is equal to our F11 or 21 because our areas are equal to. Area 1 is equal to area 2. Okay, and we want to find view factor 1, 2 between these two cylinders. And so for this question, one thing that I had struggled a little bit with this is the way this is drawn. It makes me think that maybe we should do the pen problems. 1 second. Because the way it's drawn makes me think we should kind of draw our cross strings like this, but that's not correct. What we want to do is similar to the example I showed in the theory part, the infinitely long part should be going kind of into the plane always. So as long as you set up your question like this, it's quite straightforward. So we have a diameter, we have an AS, and we're going to draw these strings kind of from one side to the other. So from as far left as you can see to as far right as you can see, and then the other way. And then we're going to connect them on the same side. So as far left to the far left, far right to the far right. And we have these two strings that are crossed and these two strings that are not crossed. And the way the cross-string method works is our F from 1 to 2 is equal to the sum of the cross strings minus the sum of the uncrossed strings actually I think it's crossed, and then all divided by the length, or sorry, 2 times the length of the surface that's being exposed through the string method. So we usually call this of surface I. And so this bottom part, this top part will be the same regardless of which surface you're talking about. This bottom part is really the thing that makes it 1 to 2, or let's call this 1 to 2 rather than 2 to 1. In this case, of course, they're the same. But for other questions, make sure you're only taking the length of the surface that corresponds to this first letter. Okay, so once we know the method, it's fairly easy. So this distance from here to here is just using Pythagoras, s squared plus d squared, square root. We know that the other one also has the same length, so there's just 2 of them. Subtract this distance, which is defined as s. Same thing, there's 2 of them, so we're going to add the 2. And then on the bottom, we're looking again for this distance. So circumference of a circle is pi d. Of course, it's not the full circumference, it's just this top part. So we're going to divide it by 2, and then we're going to multiply it all by 2, which which of course will cancel out. So simplified down slightly, our final answer will be 2. We're going to factor out the 2 on the top. S squared plus t squared square rooted minus s divided by pi d. And that's all there is to it. So it's a very elegant method, but only for a fairly limited use type. Okay.